All right, so let's draw the free body diagram for the block. So if we think of an M1 block, we have gravity, M1G. You have tension pulling up. And then which way is the acceleration? The acceleration, let's assume that, M2 is bigger. So let's assume that this is going to go up, this is going to go down, and this is going to have an angular acceleration clockwise. So we'll make up the direction of the acceleration and the positive direction. M2 has the exact same free body diagram, almost, right? Just M2G as gravity, and then only the rope is touching it, so T2 is up. But the acceleration is down. Now, is it the same acceleration? Only if it's the same rope are they the same acceleration. Yeah, it's a light cord. It's the same rope. Now, why are the tensions different? The tensions were the same across the pulley when you went around the pulley, because we assumed that in Unit 2, when we did earlier stuff, we assumed that the pulley was very light. It was easy to rotate and torque, so you didn't need a net torque to cause it to have angular acceleration. But now that we are considering the fact that it takes some amount of torque to cause this thing to rotate, we cannot have them have the same tension. Otherwise, this thing will not rotate at all. So that's why even though it's the same rope, we use two different tensions here. Now, the physical mechanism is actually friction in here that's actually causing the tension to change. Because if you do free body diagrams of the rope in there, there's actually friction that's kind of interacting there. So we don't get into that. That's kind of a little bit more advanced, but it's really the friction between the rope and the pulley that's actually causing the tension to change. Okay. So and then let's do the pulley part. Let's do our extended free body diagram. So I have gravity. The ropes are touching. T1 is pulling down on this side. T2 is pulling down on this side. And then, the axle's holding it up in place. And it's just going up. There's no X component because the net force would just be 0 in the X direction there. Okay, so that's that. And then the angular acceleration is this way, which will make the positive direction for this object here, for the pulley here. Okay, write down the equations here. When I do F net equals MA, we'll say T1 is up. So it's T1 minus M1G is equal to M1A. And then this one will make down positive because the acceleration is down. So let's say M2G minus T2 is equal to M2A. Okay, because down is the positive direction. So that makes that one positive, and T2 is in the negative direction. And this one, we have to identify our axis of rotation if we're going to use the net torque. Neither the axle or the MG exert any torque, but we have T1 and T2. And if you think about the R vector here, we would say R times T2 minus R times T1 is equal to I alpha. Okay, why? Because this is a clockwise torque, so it's going to be positive, because I said clockwise is positive. This is a counterclockwise torque because it would cause the pulley to rotate counterclockwise, right? And so that's a negative torque, and that equals I alpha. So those are our equations here. What is the linear acceleration of the system, assuming the pulley's axle is negligible friction, and determine the tensions involved. So let's plug in some numbers here. We're going to have T1 minus M1. M1 is 10 times G, so that makes it 100, equals 10 times A. Then this is M2, 20. If we use G of 10, that's 200. Minus T2 is equal to 20A. And then this one, we're going to use the fact that A is equal to alpha R. Okay, and that's because the linear acceleration here matches the angular acceleration, right? Or alpha is equal to A over R, which makes this I A over R, and you can multiply by R, you get R squared T2 minus R squared T1 is equal to I times A. And what's the radius of this thing is 0.2, so 0.2 squared is 0.04. T2 minus 0.04. Actually, let's divide the R squared to the other side, just because it's probably easier to solve. So T2 minus T1 is equal to IA over R squared, which is 0.16 A over 0.04, or 0.2 squared, and that's equal to 4A. So then we're just going to add these equations up, because if you set them up like this nicely, if you add them up, all the tensions will go away, if you set it up the signs correctly. Otherwise, you have to make some adjustments. Minus T2 is equal to 20A, and then T1 minus 100 is equal to 10A. And then you just add them all up. The T1s cancel, the T2s cancel. You get 200 minus 100 is 100. And that is, what, 34A? So the A is equal to 100 divided by 34, which is 2.94 meters per second squared. And then you can now solve for the tensions. T1 is equal to 100 plus 10A. And you just plug in the A in there. So times 10 plus 100, I get that's equal to 129.4 newtons. And then T2 is equal to 200 minus 20A. Just rearranging that equation. And I get 141.2 newtons. And as you can see, the T2 is greater. That's what causes this thing to have angular acceleration there.